Here is the next example. In this example, we're finding the resonant frequency for the following circuit. Okay, it's a different circuit with RLC parallel combination. Okay, to find the resonant frequency, make sure there is at least one inductor and one capacitor in the circuit. Then only there will be resonant frequency. If there are only resistors and inductors, no resonant frequency. Resistors and capacitors, no resonant frequency. There must L and C in the circuit. There must be L and C in the circuit. Okay, now to find the resonant frequency, first thing I'm going to convert this into j omega, so frequency domain. So this is 1 over j omega, this is 2 j omega, that's 2 ohms. Okay, now I need to find the total impedance. These two are in series. That series combination is parallel with 1 over j omega. So I'm going to call this as Zx and I'm going to call this as Zy. Okay, so Zx equal to 2 plus j2 omega. Now this is parallel with Zy. Zy equal to 1 over j omega. Now Z total equal to 4 plus Zx parallel with Zy. Okay, all I care for the imaginary part, so I really don't need to worry about this 4 ohms. That's the real part. Okay, so 4 plus Zx is 2 plus j2 omega times Zy. So since these two are in parallel, what is the formula? Zx times Zy over Zx plus Zy. So I'm going to use that formula. Okay, 1 over j omega over 2 plus j2 omega times, or plus, sorry, 1 over j omega. Now the total impedance equal to 4 plus 2 plus j2 omega divided by j omega over, so I'm going to, this is 1 over j omega in the denominator. So to make this j omega as a common denominator, or make it as a denominator for every term, I'm going to do the LCM. So j omega, it's a 2j omega plus j square 2 omega square plus 1. Now these two get cancelled out, so we'll end up with Z total equal to 4 plus 2 plus j2 omega over j square is nothing but negative 1, so negative 2 omega square plus 1 plus j2 omega. Now as I mentioned, make sure that there is no imaginary term in the denominator. So I need to eliminate that j in the denominator. So what I'm going to do, I'm going to multiply this with complex conjugate. So minus 2 omega square plus 1 plus, oh, here I have plus, so this must be minus here, minus j2 omega divided by minus 2 omega square plus 1 minus j2 omega. Okay, so this is going to be 4 plus, in the denominator this is a plus b times a minus b, so we'll end up with minus 2 omega square plus 1 whole square. Okay, so this is ab, so ab, so a plus b times a minus b, which is a square minus b square, right? So this is a square, what is b square? Minus j2 omega whole square. We know that j square is nothing but negative 1, so we'll end up with, in the denominator, a positive number. So Z total equal to minus 4 plus minus 2 omega square plus 1 whole square plus 4 omega square. Okay, I'm not going to expand this. I'm not worrying about this calculation at this point. Okay, if needed, I might need to expand it later on. My goal is I want to find out the imaginary part and separate it. Okay, so when it comes to the numerator, this 2 plus j2 omega multiplied with this whole thing. Okay, so 2 times minus j minus 2 omega square, which is a real number. I'm not going to worry about it, but I'm going to write it down here. okay, plus 2 times 1, that is also real number. I'm not worried about that. Now I'm going to multiply this with j2 omega, this part, so which is minus j4 omega cube. Okay, I have the imaginary part, so that's the reason I calculated this. So this part has importance because it has imaginary part. So make sure you write it down properly, correctly with every sign, and you do the multiplication. Okay, now j2 omega times minus j2 omega, which is minus j square 4 omega square. We know that j square is nothing but positive. J square is nothing but negative 1, so this is going to be real part. Don't need to worry. Okay, and I forgot to add this j2 omega plus 1, j2 omega times 1, so which is plus j2 omega, and the last part is 2 times minus j2 omega. Okay, you might do it differently. Even I usually do it differently. I don't know why I followed this method, but yeah, minus j4 omega. Okay, now take the imaginary part. So this one has j part, this one has j, this one has j. Okay, I'm going to separate them, so that way I can write down the imaginary part and real part. So z total equal to 4 plus, that's a real part, and another real part is minus 4 omega square plus 2 plus 4 omega square, because minus j square is nothing but 1. Okay, divided by minus 2 omega square plus 1 whole square plus 4 omega square. That is the real part, and imaginary part is I have minus j 4 omega cube plus j2 omega minus j4 omega over minus 2 omega square plus 1 whole square plus 4 omega square. Okay, now I separated the real part and imaginary part. This whole thing is real and this whole thing here is imaginary part. So I'm going to make the imaginary part equal to 0. Okay, if I pull the j outside, which will be 4 minus 4 omega cube plus, this is plus 2 omega minus 2 4 omega, so plus 2 omega minus 4 omega, it's going to be minus 2 omega over minus 2 omega square plus 1 whole square plus 4 omega square. This part must be equal to 0. So if I pull the minus, if I take the denominator to the other side, and at the same time I'm going to pull minus omega to the outside, so minus omega, so or minus 2 omega to the outside, it's going to be, what are we going to have? It's going to be 2 omega square plus 1 equal to 0. Okay, so if I take it, minus 2 omega must be equal to 0, so omega could be 0. Another one is 2 omega square equal to minus 1, so omega equal to square root of negative 1 over 2, that's imaginary part. Okay, so omega, which is angular frequency, will not have a it will not have an imaginary part. Okay, so for time being I'm going to take this as answer, radians per second, but in reality there is no resonant frequency for this circuit, or I would say 0 is the actual radians per second, actual resonant frequency for this circuit. This is the answer, omega equal to, even though I have another answer, omega equal to square root of minus 1 over 2, which is the imaginary number, and omega naught never be a imaginary number. And I forgot to mention that here, whenever we make it equal to 0, it's going to be omega naught. Okay, so omega naught equal to 0 radians per second. But in the exam, I need to see both answers and pick the right answer. So this is the right answer. Okay, remember one important thing: omega naught will not be a negative number and will not be imaginary number. Okay, thank you. I will solve one more example in the next video. Thank you.